One of the more interesting applications of integration that I can do in a fairly straightforward fashion is the idea of calculating a volume. But let me start backing up a little bit into regular geometry. Think of a box. What's the volume of the box? Okay. I'm going to hope that you mean height this way. Which one's length, which one's width? I don't really either, so we'll just go like that, right? Okay. How about a cylinder? What's the formula for the volume of a cylinder? Now, this particular example is a right circular cylinder. The hell do I mean by those things? Circular because the bottom and top are circles, and right because the base makes a right angle with the side. So the angle here is a right angle. Anybody know the formula for the volume of a cylinder? Aha. Where R is of the circle in question, right? Hey, wait a second. If I think of both of those as thing times height, I can actually make the following general statement. Given any shape, now I'm going to have to try and reproduce this shape exactly up here, so we're going to assume I do an okay job of it. Assume those are the same shape. A right cylinder over any shape is going to have volume equal to the base area times the height. As long as it is exactly the same shape all the way up. So I could think of like a cylinder over a parabola. Here in 3D, I'm going to picture myself standing at the origin with my arms outstretched along the axis. My right hand is on the x-axis and my left hand is on the y-axis. So if I'm standing here, then this will be the x direction, this will be the y direction. And if I'm actually standing in the corner, x, y, z comes out the top of my head. I tend to think of this by using my right hand. Point your first finger at me. Stick out your second finger in the direction of the palm of your hand and your thumb up. 1, 2, forefinger, second finger, that's x and y. That's exactly this picture. I'm just looking at it askewed, so I not just look straight down the dot of the x-axis. For that reason, this is called a right-handed system. The x is on my right hand, and I use my right hand to represent it. If I draw the graph y equals x squared, that's a parabola. but it lives in the XY plane. We can picture that like I do it on the floor. So let's say I go from -2 in the X direction to +2 in the X direction. That means I'm going to cross the Y-axis at 4, right? Because if I just drew X and Y, it would look like that. I'm going to call this my base area. Just to be sneaky about it, I'm going to write that letter B in this picture, in the same orientation. So you see how I slide it out and turn it so it's standing up? I can think of a cylinder over this shape. Page 438, there. There's my cylinder whose base is a parabola. I promise I'm a really crap artist. So that's why I really want you to see the picture in the textbook here as a better image. But I can absolutely figure out the area of that base. That's the area between two curves. And that's what we did yesterday. So I can tell you the area of this, and then I know how high it is. I go up 3 or up 5 or whatever it is, and I can use this idea. Does this make sense? Kind of. What happens if my area isn't the same all the way across, or in this case, up and down? Said I would do it yesterday. I couldn't find myself a good baguette. I want you to picture a loaf of bread. If I bake a loaf of bread not in a pan, what happens? Well, the ends are a little smaller. It's kind of bigger in the middle, kind of spreads out and comes back down, right? So again, crap art. I have some sort of shape on this end, another shape on this end, and then I've got this sort of loaf in the middle. And it's different thicknesses, different heights. Instead of drawing it up and down the z-axis, I want to picture it like it goes in the direction of x. Okay. Take a knife, cut a slice. Well, technically, you'd have to make 2 cuts, right? Cut a slice of bread, you need 2 cuts. But when I make a single cut, I'm going to get some shape in the middle of my loaf of bread, right? I want you to picture this standing up this direction. I cut through the bread with a plane, my knife, and I get this shape on the end. Again, I'm a crap art person. Here's this loaf from end to end, page 436 again, 446. I've got a shape here and I got a shape here, and I go along the x-axis and I make a slice, and there's my slice of bread. This particular slice happens at some x value. And I might as well tell you where the edges of my bread are. The loaf of bread goes from x equals a to x equals b, start and end. But if I picture a slice of bread, what does a slice of bread look like? I don't care if you take it from this loaf or not. The slice of bread has got a thickness to it, right? But the shape on the top of that thickness and the shape on the bottom of that thickness, if I looked at it like this, wouldn't they look just about exactly the same? Not perfectly, but they'd look really close, wouldn't they? So I can think of a slice of bread like this. If I want the volume of that piece, I need to know the area of that slice, and I multiply by the thickness. Best things in sliced bread, I slice up my bread, and I can picture a whole bunch of slices just stuck together. But each slice has a thickness and some area that corresponds to where I was along the loaf when I made that slice, right? So here I made fairly thick slices. That's not a very good approximation of the size of my loaf of bread, is it? I lost some stuff because clearly this is curved here and this is kind of jumpy. How could I get this to be a closer measurement of this? What could I do to my slices to make this look more like this? I could make more, make them smaller, make them thinner, right? And if I use more and more and more slices, I'm really doing a total volume. Wait a second. My total volume is the sum of the volume of my slices. I don't know how many slices we're going to have. So I'm just going to pick a number. I'm even going to use a variable. I'm going to say we're going to have from 1 to n slices. I'll write the volume of a slice, volume of the slice at some given x value. But y'all just told me I should use more and more and more slices to get a more exact representation, right? What would be the ideal? How many slices should I use to make it perfect? I should let my number of slices go off to infinity. Wait a minute. The limit, as n goes to infinity, of a sum of the volume of my slices. But I said I was going to think of each slice like it was a cylinder. But my cylinder is going in the x direction. This is a very bad slice of my round loaf earlier. I need to know the area at this point, and then I need to multiply by the thickness. Thickness is a little change in x because this is the x direction. Hey, wait a minute. I've seen this expression before. What kind of an expression is that? It's got a name attached to it. It's got a person's name attached to it. That's a sum. Whose sum? That's one of my Riemann sums. And that means that this is a definite integral. This volume can really be done by integrating, as long as I know this area function. And that area represents a piece of my shape. Okay, hang on a second. I'm going to create a shape by making slices. Here's a circle of radius 1. And what I want you to do is at every x value, I want you to build a square or a triangle. Let's do a triangle. We're going to make a triangle. I'm going to make a triangle for each x value. And not just any triangle, an equilateral triangle. So living on this line right here is a triangle. It's sticking up at us, out of the page. Make sense? It's kind of weird to picture. The triangles that are all the way over to the right, they're going to be very small, aren't they? And the triangles in the middle, they're going to have bigger bases, so they're going to be bigger because equilateral means all the sides are the same. And the triangles that are all the way over here on the left, they're going to be pretty small also. So when I build this shape, and I can take this to a 3D printer and physically build it, when I build this shape, I end up with this. Now take a little bit of a closer look at this particular shape, and you can actually see the triangles in it. There's a triangle very close to the edge of the x-axis. And you see there's another triangle there, and another triangle there, and its bottom is in the circle. There's the circle in the xy plane. I want the volume of this thing. All right. So I think of a slice being made. And that slice, when I pull it out, is going to be an equilateral triangle. Two questions. First, what's the formula for the area of a triangle? Second, how can I figure out the measurements needed to find that area in terms of this x value? So let's start with the beginning part. It's formula for the area of triangle. 1/2 base times height. So this is the base, and this is the height. Perfect, wonderful, fabulous. Two problems. What's the base? What's the height? Oh, crap. Oh, wait a minute. The base here, that's the length of this little line segment, isn't it? I took this triangle out and laid it down. That means this piece right here is this line right here. So my question to you now is, how long is that line? The answer is top minus bottom. So I need a y value for the top. I need a y value for the bottom. Clearly, that's going to depend on what my x is, yes? But I can write it in terms of x. What is the equation of the top of this circle? If I asked you to graph that on your calculator, you'd have to write it y equals, wouldn't you? So what's y equals for that point right there? You've got the equation for the circle. So what's the top part of the circle? Take this equation, rewrite it y equals, what do you get?
Plus or minus 4 minus x squared.
So which is the plus part and which is the minus part? And I'm going from the top to the bottom. So the base is the top minus the bottom. Yes? Here's the best part. That just becomes addition, and I get two of them. So when x is fairly close to 1, that's a very small length. And when x is fairly close to 0, that's a fairly big length. Makes sense. In the middle of my circle, it's taller top to bottom than it is at the edges of my circle, going left to right. Now, height. How do I get the height? You need some trigonometry and some geometry to be able to do this part. To do Pythagoras, I need a squared plus b squared equals c squared, right? Great, fabulous. The problem is, do we know what those values are? I'm trying to find this one.
Is it left, C equal B, A equal part of B?
Great. And that means that h is, well, Pythagoras would tell me that h squared plus a squared is c squared. So h squared is c squared minus a squared. Square that, what happens? What happens when you square these? And squares the two. So here, I'm going to get 4 times 1 minus x squared. And here I'm just going to get 1 minus x squared. 4 thing minus thing is 3 thing. And that means that h is the square root of this. Square root of 3 times the square root of 1 minus x squared. Now put those two together. 1/2 base times height. The base right there. And the height right here. Two wonderful things happen. What are those two wonderful things? Square roots cancel, and the 2.5 cancel. Well, now that's a formula in terms of x, isn't it? This is an area function. Just like when we were doing maximums and minimums, optimization problems, we had to find a function of something, one variable, so I could find a maximum or minimum by taking a derivative. But now, I don't want to take a derivative. I want to do an integral. Question. I need to know where I start and where I end. Where does my shape start and end? If I'm thinking of it in terms of x. What is the furthest left you can go? Be inside this shape. And the furthest right? There you go. And that means I can actually do the volume as an integral. First of all, what do I do with the square root of 3? It's a constant, but it's being multiplied by all of this stuff, right? So I take that constant and move it out front. And that is a much easier integral for me to do. Because now I have a 1, and I'm integrating that. What do I get? It's the integral of 1. Sorry. What's the antiderivative of 1? X. And the antiderivative of x squared? Plug in 1, plug in minus 1. Plug in 1, I get 1 minus 1/3. Plug in negative 1, I get negative 1 minus negative 1/3. What's 1 minus 1/3? And then negative 1 minus negative 1/3 is negative 2/3. But I'm subtracting a negative, which means I add. So just like I could find the area of a shape by making it in little slices, I can find the volume of a shape by making it in little slices. B.
Why is it 2 and 3? 1 minus negative 1.
But it's negative 1 minus negative 1/3, right? Those cancel. Then this is negative 3 on 3 plus 1 on 3, negative 2 on 3. And this is really where calculus kind of comes together. When I did derivatives, I did them as tangent lines. I thought of them as little bitty changes getting closer and closer together. And all of my derivative idea was about moving things to be really tiny slices. pieces of X. And now I'm adding up tiny little sliced pieces of X. I get areas, I get volumes. If I can decompose into little bitty slices, I can find a way to do an integral. Now, I will freely admit, the way I constructed this shape was a pain in the ass. Here's a circle, we're going to build triangles on this thing. Who does that? Well, if you build roofs with trusses, a truss is a triangular shape that goes across the top of the building that's designed to hold the roof boards on. I built a roof. More often than not, though, I'm going to rig problems so that I think of the cross-sectional area as something nice and easy. I'm going to take a curve. I actually brought this curve with me. Here it is. It's a shape. I brought it on purpose. I want you to take this shape and I want you to spin it around the x-axis. Now, my goal, once I've done this revolution, is that I will have a solid object. I want to know how big it is. So I'm going to take this shape and I'm going to twist it around. And I'm going to get a solid object. And I deliberately went out and cheated. I twisted it. There's my solid object. What's its volume? What the fuck? Let me go back to this for a second. I have this idea, right? I spin this around the x direction. And I get this shape. Now it won't fall apart on me. I'm going to find the volume of this thing. I'm going to make a drawing. When I spin this around, I end up with another copy down here, right? Pick an X point. Do you want it to be close to the y-axis or closer to this other end? I don't care. Pick a spot. So closer to the y-axis. Now, let's pick a point on the curve at that value. So I go up here and I have a dot. And I want you to picture what happens to that dot. We spin it out and back, right? It goes around the x-axis. Like I started at some point on my curve, and I go around. Okay. Let's draw that circle. I go around, I hit the curve down here, and I come back up the backside. I am now looking at that circle, end on. So what's that dot? It's the x-axis. That's right here. Okay, if that's the x-axis, where's this little stick? Cut my fingernails, I can't get the little pry apart. That little stick came from a point on my curve, right? That's this spot getting spun around. All the way around to the bottom and then back up. That's a spot on the curve that makes this dot right here up here. And I've got that. This is the radius of my circle, isn't it? And that means that the area of this circle is form the area of a circle. Really? Come on, what's the area of a circle? Pi r squared. But that radius came from up here. And on this curve, I have an equation. This r is a y value. And I know the equation for that y value. And that means that this area can be written as a function of x. If I want the volume of this shape, I've now cut it into little circles. And I've stacked those circles from the left to the right. And they change their radius as we go from left to right. But I can add up all those slices. When I add up all those slices, I'm integrating that function that is the area from one end to the other. Now the only other thing I need to know is where we start and where we end. What are the A and the B in this problem? When the y of the equation is equal to 0. Because if I go back up to this picture, that would be here and here. Down here would be this spot and this spot. 4x minus x squared equals 0. What x values make that happen? And zero and 4. I've added up my slices, but all of my slices are individual circles. So I have a stack of coins of varying diameters as I go from left to right. And that's all an integral is. It's a sum. That's what that long symbol is. It's the letter S. I'm adding up. I just have to do some algebra first. I can take the pi. Pi is a constant. What can I do with a constant? Like my square root of 3. I can jump it out front. Now I just have to multiply that out. 4x minus x squared all squared. So I'm going to get 16x squared. Then I'm going to get 4x cubed and another 4x cubed. And then minus and minus becomes plus x to the 4th. And once again, I am absolutely thrilled because this is power rule. Yay! Now I just have to plug in and get an answer. Plug in 4, plug in 0. Oh, I forgot another set of parentheses. $64, $128, $256, $512. I'm going to leave that. 64, 128, 256, 512, 1024. Now it's just a matter of common denominatoring and actually getting an answer. Or you can give me a decimal if you want, but it's going to be a repeating decimal. It's going to suck. I have a calculator. With a pi in front of it. 512 over 15 pi. Cubic whatevers, because it's volume, right? Cubic inches, cubic feet, cubic meters, cubic centimeters more likely. I mean, after all, it is a football. I got it at Harvey Supply Store as bunch of Super Bowl decorations. A long time ago. This idea is the same one we were just using, but my slices were a lot simpler because they were circles. This type of shape is called a volume of revolution or a solid of revolution. And the best part about it is that it's always a circle because I'm rotating around something. Always. Mostly a circle. Might be something else. Questions? Same setup, different curve. Again, just like with the areas between curves, just like with my definite integrals in general, I'm going to start with a picture. What's the graph of the square root of x look like? But it only goes out to 1 because it says from x equals 0 to x equals 1. And I'm going to rotate that around the x-axis. So again, I'm going to go this way. So that means that this top curve is going to come out of the piece of paper and then hit the piece of paper on the other side, down here. We're going to go out, come down, and then back up the other side. Like a bowl turned on its side. I find it helpful to draw the little stick like we did last time. So I'm going to pick some x value in the middle, and I'm going to go up. I'm going to make the circle. I'm going to draw that little slice this way. What's the radius of that circle? It's whatever the y is. Y is the square root of x here. Which means finding the area of the circle. The area of the circle is pi r squared. R is the square root of x in this case. Well, that just got a lot easier. What happens when you square the square root of x? Poof. The pi comes out front again. I integrate. Plug in 1, you get 1/2. Plug in 0, you get 0. Ta-da! This sort of decomposition is referred to as a volume by discs. Because if you think of each of these slices, each slice is a thin disc, a coin, stood on edge. Balanced in our curve. And then I just take it out and lay it down. Now, Depending on our region, we may want to do this integral differently. The difference here is subtle, but important. The first thing I want you to do is the same thing I did in the previous problem. I want you to draw a picture of the region.
Division or collapse.
Oh, absolutely. Because I'm giving you the boundaries of this region. So the graph y equals x cubed looks like this, right? What's the graph y equals 8 look like? A horizontal line. What's the graph x equals 0 look like? X equals, not y equals. So it doesn't go horizontally, it goes vertically. As a matter of fact, x equals 0 is the y-axis. I have a bounded region here. So I'm going to redraw this without this little bit tail down here. I'm just going to draw it right over here. And now I'm rotating this. But I'm rotating this around the y-axis, not around the x-axis. So my direction has changed. I'm not rotating this way. I'm rotating this way around the y-axis. This is standing up, not laying down. Okay. That means instead of going around here, we go around here, which means I fold this over from right to left. It's going to spin around this way. So now when I picture that coin that I was drawing earlier, I promise these do balance. It's going this way. Come on, stand up. There. So let me pull this circle out like I did before. I take this circle out. And there's the radius. But the radius goes this way. It's not a y value anymore. What kind of a value is it? And what's the left x value? 0. So it's whatever the x value is on that side of the curve. Okay, my radius here is an x value. Okay, wait a minute. This is the equation here. It's right minus left, not top minus bottom. We did this at the end of class yesterday. I need to take this equation and rewrite it to be x equals. And when I do that, what do I get? Or y to the 1/3 power. Now, I'm going to do this same idea. I'm going to add up all my little circles. I'm going to integrate, but now it's a of y dy because the thickness of my circle is along the y direction, not the x direction. So it's dy instead of dx. By the way, if this bothers you, if this pisses you off to no end, you are welcome to take the picture and turn it 90 degrees. I just have one other question before I can set up the integral here. I need to know the y values, where we start and where we end. So what is the lowest y value I can use and be part of this region? 0. And the biggest one is 8. And that's exactly why I wrote it down, Dean. So my volume is the integral from 0 to 8 of pi r squared. And since r is in terms of y, I integrate dy. Hey, wait a minute. Y to the 1/3 squared. How does that simplify? Power of a power. What do I do with my powers? I multiply them together. But that's power rule again. Yay. I get y to the 5/3 power, which means I get a 3/5 because it would be over 5/3. And I have to take it out, flip it. And now I can plug in. A 1/3 power is a cube root, right? What's the cube root of 8? So this is pi times 3/5 2 to the 5th minus 3/5 0 to the 5th. So I get what's 32 times 3? 96. 96 pi over 5. Phew. Now I could take this same region and go around the x-axis. I'd get a different volume. But look at what happens if I try and draw the picture of this same region going around the x direction. I'm going to take this region and I'm going to go around the x direction. Down here, I get that, right? Pick an x value other than 0 and 2. 1. So if I pick the x value 1, I'm right about here. Hey, wait a minute. My piece, if I start going up, to try and draw that radius, it only has to happen in the region. It doesn't touch the axis anymore. This goes out to here and then up the back. But so does this. I don't get a disc anymore. If I pull this shape out, I get two circles, which are concentric. The area I'm looking for is between the two circles. If I'm being a math geek about this, I'd call this an annulus. But if I'm being a human being about it, this is called a washer. Like a washer that goes on a nut and a screw and a bolt. This is a washer. It's two circles, one inside the other. Wait a minute. What's the area I've shaded? I now need two different radiuses. I need the radius for the inside, and I need the radius for the outside. So I have an R in, and I have an R out. And the area is the difference in the two circles. So even though I'm still using circles, I end up with something more complicated because I have to have two circles, an outside circle and an inside circle. And I got to subtract the two away. If I physically built this, it would have a hollow section in the middle, wouldn't it? This right here would be some sort of hollow center. If you do wood turning or watch people do wood turning, that's exactly the cutaway I would make with my scraper or my awl. All right, wait a second. Which of these two curves is going to give me the outside radius? From the axis to get to the outside curve. The outside curve is the horizontal line on the top, isn't it? From here to here, that's my outer radius. Top minus bottom. Inner radius goes from here to here. So I can actually do this, but it's not one integral anymore, it's two. Oh, I just wrote those backwards. Ah. It's the outer radius minus the inner radius. I can't do it in the other order. That would be bad. Now, again, I'm the kind of person who likes these sorts of pictures. So I imagine I've got a region with an outside and an inside. And when I spin it around, I get this washer shape. And as long as I know which curve is the outside one and which curve is the inside one, I can make this work. It doesn't have to be around the axis. We could go around a different line. I could take this same shape, and instead of rotating around the x-axis, I could rotate around a horizontal line up here. Spin this around like the line y equals 2. And if I do that, I get this shape. And there's my axis at y equals 2. Notice this changes which one's on the inside and which one's on the outside. Because now the inside one is the straight line, and the outside one is the curved side. I can do these things in general. I can do them vertically as well. The thing I find most important in all of this is to write out which is the outside radius and which is the inside radius, and to physically mark them in our diagrams so we know where they are. So here is where I am begging you, make sure you have a graphing device in front of you, because the easiest way to figure out which curve is which part is to draw a picture. Questions? This works really, really well most of the time. There are exceptions. And in some cases, it's a matter of whether or not I can write the function I want in the variable I want to use. When I'm going this way around a vertical line, I want to write things in Y. When I'm going around a horizontal line, I want to write things in X. Here it's in X. Here it was in Y. I was going around a vertical line here, I went around a horizontal line here. But what happens when doing that is hard? If I wanted to go around the y-axis, I'd have to write this x equals. I don't know how to do that. So I'd really rather not do it. Well, if that's the case, then I can't use discs. I can't use washers. I need another way to cut up my shape. Now, we can cut up our shapes just about any way we want. The pictures that we did, this one was cut into triangles. But I could just easily cut something into squares, or cut something into little wedges. There are all sorts of decompositions depending on the shape of my object. And I'm 100% going to tell you that this is where I beg you to draw these pictures, because there is nothing better than physically sitting down and slicing up a lump of clay to figure out what this shape is. But I don't want to do pottery class in here. Do that down at the shack. I will see you all tomorrow, where we'll look at our next case. Have a wonderful rest of your day.